Okay, in this next video we want to look at the basic electron configurations for elements at the beginning of the periodic table. We finished off the previous video looking at the orbital shapes for the p orbitals. A couple of key things to remember. Each energy level has that energy level number squared as the total number of orbitals available in that energy level. So the first energy level has one possible orbital, the second has four, the third has 9, the fourth has 16. Within each energy level, the first orbital is always S-shaped. The second, third, and fourth orbital are always P-shaped. It's a set of 3. The next 5 are going to be D-shaped. They're a set of 5. The next 7 will be F-shaped. They're a set of 7. And that will basically cover the orbitals that we will be dealing with. So they go by the odd numbers. S has 1 possible orbital, P has 3, D has 5, and F has 7. Now when looking at electron mapping, we are looking at some basic rules that were discovered for deciding exactly where the electrons are located in the atom. The key thing is that each electron must have a unique set of quantum numbers. If you remember from earlier, the 4 quantum numbers, principal, orbital, magnetic, and spin. Principal being the energy level, orbital being the shape of the orbital, magnetic being the axes that we are located on, and spin being plus or minus spin for the electron. So any electron cannot have the exact same basic address set of quantum numbers. And it is most stable when it's in the lowest energy state possible, when they're in the lowest energy levels that they can possibly be in. This all comes out to something called the Pauli exclusion principle, and this is a picture of Wolfgang Pauli here on the screen. In a given atom, no 2 electrons can have the same set of 4 quantum numbers. Now, if an orbital is defined principal quantum number energy level, orbital quantum number shape, magnetic direction, the basic structure of the orbital will be defined by those first 3 quantum numbers. The last quantum number, plus or minus spin, gives us 2 options for an electron within that orbital. After those 2 options, you would start doubling up on quantum numbers. So the key thing that comes out of this Pauli exclusion principle is 2 electrons per orbital. At most, we can have 2 electrons per orbital. Very likely, we can have anywhere from 0 to 2. Now, we're going to go through a number of elements here and look at the number of electrons in the basic electron configuration. Now, we know hydrogen in its neutral state has 1 electron. Now, there are 2 ways to write electrons. There's what's known as orbital notation. In orbital notation, you draw the orbital as either a line, or you can make it a box. Doesn't matter which one. You put the label of the orbital underneath. So the first orbital we always come to is the first energy level, S-shaped. Then you put an arrow in the box for the 1 electron. So this would be the orbital notation. You'll see me more commonly, rather than writing boxes, write it this way. And actually I only write half arrows instead of full arrows. Now it doesn't matter which one you choose to do. I think the half arrows is a good reminder to myself that there are only 2 electrons available in an orbital. So once you have a full arrow, the orbital is full. The other is known as electron configuration notation. Here we write out the name of the orbital, the 1s, and we put a superscript for the number of electrons. So hydrogen's electron configuration can either be 1s with a arrow in it, or the 1s1. Helium has 2 electrons. So in the orbital notation, we have the 1s, we have 1 electron with positive spin, 1 electron with negative spin. You always see me draw these ups, one right side up, one upside down to show the 2 spins. I have seen it done where you draw 2 arrows both pointing up, both full arrows. There are lots of different ways you'll see this written, but this is just the way I prefer to do it because I think it helps me remind me there's 2 different spins and that now that orbital is full. Or in the electron configuration notation, this would be 1s2. Now lithium has 3 electrons. So it's going to fill up the 1s orbital. There's only room for 2 electrons within an orbital. Now we need to go to the second energy level, and the first orbital in any energy level is S-shaped. So we have 1s and 2s. In the electron configuration notation, we'd write it 1s2, 2s1. You see, if you count these numbers here, the total is 3, which is the total number of electrons in the atom. If you count the arrows above, you should have 3. Beryllium, 4 electrons. So we do 1s, 1, 2, then 2s, 1, 2. Or 1s, 2, 2s, 2. Next one, boron. Now boron has 5 electrons. So we're going to fill up the 1s orbital. We always start from the ground state, which is the lowest energy. So work our way up in terms of energy. We fill up the 2s. After 2s, there are 3 more orbitals that are in the second energy level. These are known as the 2p. You can write it 2px, 2py, 2pz, or just write 2p under all 3 lines, under the mix of the 3 lines. We only have 1 more electron, so we'll add 1. But we have to do these as a group because these are a group of 3. They always come together as a group. 1s2, 2s2, 2p5. Now when we move on to carbon, carbon has 6 electrons. We're going to add 1 more into the 2p orbitals. If there's another rule that we need to follow though. This is known as Hund's rule. Hund's rule is that the lowest energy electron configuration is when you have the maximum number of unpaired electrons for a degenerate set, meaning for a set that all has the same energy. So the 2p set of orbitals that we saw here, 3 orbitals, the lowest energy state is for them to be unpaired. Now, remember, electrons are negatively charged. They repel each other. So if we can spread them out within an equal set, then we want to spread them out. So this is the 2p. We'll put 1 in the first orbital. We'll put 1 in the second orbital, rather than doubling up in the first orbital. It's kind of like if there were 3 equal rooms in your house, and you and your sibling had to choose the rooms to stay in. You probably wouldn't double up in one room and leave the other 2 empty. You'd probably spread out and each take 1 until they were all full. If there were 4 siblings, then somebody would have to double up. In the electron configuration notation, 1s2, 2s2, 2p2. Nitrogen, 7 electrons, 1s2, 2s2, got the 2p set. Now we're going to have 3, and they're going to go 3 into each of the individual p orbitals. You see this clearly in the orbital notation. You do not see this clearly in the electron configuration notation. You do need to know how to do both notations. Oxygen, 8 electrons, 1s2, 2s2. We're going to have 4 now in the 2p. 1, 2, 3. Now we're going to have to start doubling up because there isn't another one in the set to spread them out. 1s2, 2s2, 2p4. Fluorine, 9 electrons. 2 in the 1s, 2 in the 2s. Then we get the 2p set. 1, 2, 3, 4, 5. And it doesn't matter which of the 3 you double up. It's just make sure there's 2 doubled up and 1 unpaired. Finally, in that second row of the periodic table, we have neon, which has 10 electrons. So 1s2, 2s, 1 and 2, 2p, 1, 2, 3, 4, 5, 6. And that fills up the second energy level. So this is all of the potential orbitals and potential electron configurations for the first and second energy level. The next video we'll start to look at what happens into the third, fourth, fifth, sixth, and seventh energy levels.